Let's talk about Klow blend. This is a combination of 4 peptides: GHK copper, BPC 157, TB500, and KPV. The goal of this blend is to support repair, recovery, and inflammatory balance through different but complementary pathways. Welcome to this page. My name is May. I work in clinical setting for about 20 years. I am an advanced practice registered nurse, and I focus on science behind cellular signaling and recovery. First, a quick foundation. Peptides are short chains of amino acids that act as signaling molecules. They help regulate how your cells respond, repair, and communicate. Let's break it down. BPC 157. This is a peptide originally identified in your gastric fluid, and it's been widely studied in preclinical models for its role in repair and regeneration. One of its key mechanisms is angiogenesis, which is the formation of new blood vessels. Now, this matters because areas like your tendons and ligaments have a limited blood supply, which is why they heal slowly. By supporting blood vessel formation, you improve delivery of oxygen, nutrients, and immune cells to the injured area, and that creates a better environment for healing. This is why you'll often see it studied in tendon and ligament models where recovery is typically delayed. It's also been explored for its role in maintaining gut lining integrity and supporting recovery after injury or stress. Overall, the pattern in the research is consistent. It supports the body's natural repair signaling by improving circulation and creating the condition needed for healing. Now let's connect that with TB500. TB500 is a fragment of tyrosine beta-4, which is involved in the body's natural healing response. It works at the level of actin, a structural protein that allows cells to move. This is important because repair requires cells, nutrients, immune signals to reach that site of injury. TB500 helps support the movement. It allows cells to migrate more efficiently into the damaged tissue, which supports repair and regeneration. It also involved in angiogenesis and tissue remodeling, so it complements what BPC 157 is already doing. One helps improve blood flow, the other helps deliver the cellular components needed for healing. Next is GHK copper. It's known for its ability to modulate gene expression, including genes that are involved in repair, inflammation, and tissue remodeling. It also activates fibroblasts, which are responsible for producing collagen and elastin. And this is why you see improvements in skin quality, elasticity, and overall tissue strength. Another interesting area is its effect on stem cells. Preclinical data suggests that it can help activate dormant stem cells in tissues and bone marrow, supporting repair and regeneration. Now, there's also emerging research looking at how it interacts with genes involved in cancer biology. Some studies suggest that it can downregulate genes associated with tumor growth and support genes involved in normal cellular repair. Now, these are still early data, but it shows how broad its signaling effects can be. GHK copper also have an antioxidant effect. It has been shown that it supports the body's defense system. It can increase activity of enzymes like superoxide dismutase and also support glutathione pathways. Now, this helps reduce oxidative stress, which is another key factor in aging and chronic inflammation. So when you look at it as a whole, it's not just working on one pathway, it's influencing repair, inflammation, oxidative stress, and overall cellular function. And finally, KPV. KPV is a smaller peptide fragment known for its strong anti-inflammatory properties. Its main mechanism is through inhibition of NF-kappa B, which is one of the key pathways that drives inflammation in the body. When this pathway is overactive, you get sustained inflammatory response. KPV helps regulate that response, bringing it down into a more balanced state. Now remember, peptide does not block. Peptide modulate. So when you look at all 4 together, each one plays a different role. BPC 157 supports blood flow and local repair. TB500 supports cell movement and tissue remodeling. GHK copper supports gene expression and structural repair. KPV helps regulate inflammation. And that's where the synergy comes in. You're targeting multiple steps of the healing process at the same time. Anyway, so now let's go to the most asked question. Let's talk about stability and the concern around peptides being combined. There are questions about whether these peptides remain stable together or if they break apart, lose potency, or aggregate. So let's break that down. First, GHK has high affinity for copper, and that means it binds copper tightly and forms a stable complex under normal conditions. Now, this bond is not easily broken in solution unless certain conditions are present. The main factor that affects this is pH. Study shows that GHK copper is stable roughly between 4.5 and 7.4. So below 4.5 is more acidic conditions, and above that is more alkaline conditions. So both of those conditions can destabilize or dissociate copper from GHK. So the key point is this: the environment matters more than the presence of other peptides. Now let's talk about bacteriostatic water, which is the most common solution that we mix with peptides. So, bacteriostatic water contains benzyl alcohol and has a near neutral pH. It does not act as a strong buffer, but it also does not push the solution into extreme acidic or alkaline ranges. So, it is generally compatible for reconstitution, but it does not actively control pH the way a true buffer system would. Another common claim is that other peptides can steal the copper. Now, for that to happen, you need a strong competing ligands like your EDTA, citrate at high concentration, high dose of vitamin C, or thiol-containing compounds like your glutathione. So these molecules have a strong chemical ability to bind or alter copper, which we don't mix those compounds on Klow. Now, peptides like BPC157, PB500, and KPV do not have that level of chelating strength, so they are not expected to pull copper away from GHK under normal conditions. Now, let's talk about aggregation or molecular crowding. Aggregation is when peptides stick together and form clumps. So this is not random. It depends on several factors, like your pH that we talk about, temperature, peptide concentration, ionic strength, which refers to the salt content, and hydrophobicity. Now, hydrophobicity means how much a molecule avoids water. If a peptide has more hydrophobic regions, it is more likely to stick to other peptides instead of staying dissolved. Now, this happens on longer chain peptides. They are more prone to aggregation because they have more complex structure and more interaction sites. Like your terzepatide, they have longer chains of amino acids. Now look at this blend. GHK and KPV are only 3 amino acids. BPC157 is 15 amino acids. TB500 is a fragment and not even the full 43 amino acid chain. So these are relatively small chain of amino acids, which lowers the risk of aggregation compared to larger molecules. Now, let's define when instability actually happens. For this blend to become unstable, one or more of these conditions usually needs to occur, like extreme pH outside the stability range, presence of strong copper chelators, oxidative or redox active environment, high heat over time, high salt concentration, repeated agitation or improper handling like shaking your vial, microbial contamination. So most instability does not happen during the time of injection. It happens during formulation, storage, and handling. And this is exactly why sourcing matters. In a pharmaceutical or regulated compounding setting, the formulation is controlled from the start. pH is measured and adjusted. Appropriate buffers are used when needed, and stability is tested over time. Now, some pharmaceutical lab runs analytical testing like high-performance liquid chromatography and mass spectrometry to confirm identity, purity, and detect degradation. So they assess for aggregation, oxidation, and any structural changes before it ever reaches you. So the takeaway is simple. It's not just about what peptides are in the vial, it's about the chemical environment they are placed in and how that environment is controlled. When the process is done correctly, stability can be maintained. Thank you for watching, and as always, educational purpose only and not medical advice. And if you like this video, please like and subscribe, and you can ask any question under the comment and I will make sure to answer that.